Hi, welcome back to this course on computational thermodynamics and kinetics of materials. This is the final class of this course. In this class, we will see a summary of this CalFAT method, the core ideas of this CalFAT method, and then we will see the challenges in it and the history of CalFAT and future directions. Right, we will start with a summary of this CalFAT method. CalFAT stands for calculation of phase diagrams. Because of its capabilities, the better name given is computational thermodynamics. The central idea is twofold. One is get the Gibbs energy database through thermodynamic assessment, and second is use the generated Gibbs energy database to calculate phase diagrams, properties, and so on. So in the first part, there are more things, that is get the input data related to Gibbs energy, which are thermochemical data and phase equilibria data. They can come by experimental means or theoretical means. Then Gibbs energy models are created to account for temperature, composition, and possibly pressure dependency of Gibbs energy. And things like compound energy formalism are used there. And then the models are fitted to the input data, fitting the model to the input data to get the Gibbs energy description. Once the Gibbs energy descriptions are arrived, compile the description into a database file readable by a CalFAT software. So this is the summary of the method. We'll see the challenges in CalFAT. We'll understand them. We'll start with an example, COCR-MN ternary system. So two diagrams for the same system are given. Let's understand them carefully. This is COCR-MN ternary diagram. This is at 800 degrees Celsius. There is no ternary sigma phase in TCHEA database. So this using TCHEA database, if this is plotted, this is how we get the diagram. You can see sigma phase in the binary side here. In COCR side, there is a sigma phase, and in the CR-MN side, there is a sigma phase here. Another black line you can see here. Okay, so they are only in the binary side. There is no ternary sigma. Whether sigma phase extends into ternary side or not, we don't know, because that's not included in the model. And what is included in the model is the terminal solid solutions, the FCC, BCC, HCP, the A13. For these phases, the solubility in the ternary regime is included, but these solubilities are also, whether they are accurate or not, we will not know unless this sigma phase extension into ternary direction is known. Okay, so if some experiments are done within this range, let's say a few experimental points are here, you can see there are these triangles, these are all equilibrated alloys. If you take these compositions, just equilibrate it and see, what you see is sigma phase in all of them. So that means sigma phase is present very much in this middle compositions of, very much in these concentrated compositions of this diagram. So this sigma phase, actually after all the assessment, this is after doing thermodynamic assessment to get the Gibbs energy description of sigma phase in the ternary regime. This diagram is improved version of this one, where you see the sigma phase going in the middle, all the way extending from one binary to the other binary. It's continuously present in this diagram. So because of this, all these solubilities also are modified. You can see A13, FCC are quite big here, BCC is quite big here, and now they are shrunk, and there is a big two-phase region coming, and the single-phase region of sigma is here. Okay, so for this sigma phase, one has to do a modeling in this concentrated region and get the Gibbs energy description of it. And this is the status of many ternaries. Although a large number of ternaries are assessed, there are still significant number of ternaries which are not assessed yet. Okay, so this is important. We need to have this ternaries assessed correctly, fully for all the phases. So that is important. Otherwise this kind of ternary systems will have problem, and obviously this ternary can be part of a higher order system. For example, if we take this AlCOCR-MnNA system, these are the two phase diagrams, the phase fraction plots of it, before including that sigma phase description of this COCR-MN. The previous slide has the COCR-MN data. Without including that, this is what we get. No ternary sigma phase data is included in this. So there is no sigma phase seen. And this side, we have this sigma phase coming. This you can see here, sigma phase appearing here. Okay. So this is about 10% of sigma, 0.1 mole fraction of phase is about 10% of sigma, and sigma being an embrittling phase, if you don't get this correctly, then we may end up choosing this alloy as a nice BCC plus B2 alloy, and possibly we'll think that it will give a good strength and ductility, and whatever we concluded based on the CalFAT phase diagram will not work out in reality. Okay, these kind of better databases are required now. To quantify such things, there was an attempt in 2015. These credibility parameters were proposed by few authors. To understand this, let's take an example of a 5-element alloy. There are 10 binary and 10 ternary subsystems present in that. Let's say there is a database with these 5 elements. Does the thermodynamic database of these 5 elements carry descriptions of all those subsystems, these 10 binary and 10 ternary subsystems? If that is not there, using it for the 5-component alloy can give wrong results. Okay? These credibility parameters basically indicate that the number of included binary and ternary thermodynamic descriptions called fraction of fully assessed binaries FAB and fraction of fully assessed ternaries FAT respectively. The point is this: the higher the values of this FAB and FAT, the higher the reliability of the database. Okay, the point I am trying to insist is this: that there is a need to make this kind of a reliability assessing parameters FAT, FAB and all. Why? Because there are many ternaries that may be missing. There are even binaries that may be missing when you make a 5-component database or a multi-component database. And if you rely on the database, if you do things like high throughput calculations, where you select compositions based on what phases are present in what ranges of temperatures, things like that, you may possibly miss compositions which are potential to give good properties. You may also choose compositions which may not give good properties. Therefore, the main challenges are this: inaccurate and unavailable thermodynamic data for several systems. And if it is so in thermodynamics, it is more so with regard to kinetics, thermophysical properties, interfacial energies and mechanical properties. Other major challenge is the assessment process itself. Okay, the time and effort are high. As I told in one of the previous classes, doing it for a couple of ternaries can become a PhD problem itself. Okay, so that is the kind of effort involved, and also it requires judgments and experience of the assessor. Meaning, this is not cup of everyone's tea. People who spend time in doing this CalFAT research, only they can get more and more refined in doing this quickly. So that is another major problem here. Okay, so we will see how these things can be addressed in the future of CalFAT. Before that, let's see the history of CalFAT. It all started in 1960s. The foundation was in 1960s. This was the first calculated diagram, CRCU-NI phase diagram by Majoring in 1957. Basically getting the thermodynamics, and from thermodynamics calculating the phase diagram. Okay, and then in 1969, Larry Kaufman and collaborators introduced the term CalFAT and started using computation power for calculating phase diagrams. That is when the first attempts are made to use thermodynamics plus computer power to do this. And then in 1970s and 1980s it grew. The book by Kaufman, Computer Calculation of Phase Diagrams, was released. Then came sublattice formalism, compound energy formalism, and first CalFAT conference was started, CalFAT journal was started, and thermocal software was started. So all these things happened in 1970s to 80s, and then more and more databases were developed, and standardization of Gibbs energy also was done. The first standardization for the pure elements was released, the SGTE Dinsdale, in 1991, and the textbook which is used to teach most of this course was released in 1998, Saunders and Medonwick. These two softwares, Pandat and FactSage, also came, and CalFAT got extended from thermodynamics to other things like kinetics, precipitation modeling, thermophysical data, etc. And as the computer power increased in 2000 and 2010s, DFT calculations became easier to do. So linking with first principle calculations to supplement scarce experimental data started, and connection to microstructure simulations like phase field modeling and process modeling also started. And more importantly, in 2011, the Materials Genome Initiative started in USA. See, as major breakthrough in science, the Human Genome Project was completed just before that. So the Materials Genome Project is to accelerate the material discovery. It was started by President Obama in 2011. And from that came the ICME approaches a little later. We'll see about that in the future of CalFAT. So when it comes to future of CalFAT, the first thing is the databases and models, the challenges that we talked about. Development of more robust databases and models for thermodynamics, kinetics, Thermophysical, interfacial and mechanical properties are all required, and if at all it can be done in a high throughput manner, it will be helpful. High throughput experiments and ab initio calculations for input generation would really help. Then coupling with multi-scale models, linking with atomistic models like DFT, molecular dynamics, and mesoscale, that phase field modeling and precipitation, and macro scale where mechanical properties can also be simulated, finite element process simulations can also be done, all towards integrated computational materials engineering, the ICME frameworks, and take to applications such as simulating additive manufacturing process and closer to real-time application simulations. Lot of research is going on in these areas, and integration with machine learning and AI is also an important direction. Automating parameter optimization, handling sparse, incomplete data, accelerating database development can all be done with the help of machine learning. And also uncertainty quantification, moving from deterministic predictions to probabilistic approaches that include error margins. You know how the input data is handled in CalFAT. So this sort of things will really help in assessing them. Right, this is a case study. For further learning, this is what you can do. Immediate learning activities after this course are this. Use the help files in Thermocalc. Open Thermocalc, go to help, go to manuals folder. Find out these couple of files. One is the example file, other one is the user guide. Okay, so these example files, you can take them and execute examples one by one yourself, seeing that file. Okay, that is one job. Second is, if at all you have doubts, you can refer to user guides. If at all you don't understand certain syntaxes, you don't know what syntax to use, how to call certain properties in Thermocalc. So all those things can be clarified if you go to user guides. Okay, so this is what you can do as the first job after this course, because this course, since you have done these hands-on sessions and all, if you don't keep doing that, it may become hazier with time. If for you to come back and use it actually for any of your applications, it will become difficult. You mean actually need to learn more thermodynamics, more kinetics, and keep using this Thermocalc software. Get a hands-on experience with this. Trying to play with the software. You can try out all these things and keep it as a strong tool augmenting your work. Okay, before closing, I want to acknowledge people. Professor Hari Kumar from IIT Madras, he taught me CalFAT. He is one of my PhD supervisors. My other supervisor, Professor B.S. Murthy, is currently director of IIT Hyderabad. My gratitudes to both of them. And Mr. Anant Krishna and Sangi Bharat Kumar, they are PhD scholars under my supervision in University of Hyderabad. They were the TAs of this class, helping me throughout this course. And of course, NPTEL team from IIT Madras. And Dr. Soumya Sridhar, she helped me with the optimization class. The example that I showed for curve fitting was basically shared by her. And Mr. Gunti Shiva is also doing PhD under my supervision. His work was shown in the high throughput calculations part. And Dr. Mukilvendan Ayasami, he helped me in setting up the studio. And the funding part came from Institution of Eminence Directorate. The camera and studio setup I have was sponsored by them. And the Dean and Faculty of School of Engineering, Science and Technology, University of Hyderabad, who supported me at various stages. And last but not least, my wife, my mother and my son. Without them, I could have not done this. And you, the students who have attended this course, all the way from physical metallurgy to thermodynamic fundamentals, kinetics, and how to put them into computers, the hands-on sessions, and how CalFAT extends to different areas. I hope you have enjoyed the journey. I hope this course is useful for you in the future. Thank you.